All right, back again. Day 3 notes. Doing a little bit more work with that sine and that cosine. So if you recall from our unit circle, the x coordinate of a point is your cosine, the y coordinate of a point is your sine. Draw and label your unit circle. Okay, so we've got, start with our quadrantals. So there is our unit circle. So looking at some questions here. Given the function f of x equals 6 times the sine of x, which of the following is true for the value of f of 60? So just like any other function, we're plugging in 60 for our x. So 6 times the sine of 60. So if I look up here at my unit circle, sine of 60 would be radical 3 over 2. So multiply those and I get 3 radical 3. Number 3, if g of a little fishy guy equals 4 cosine minus 2 sine, then g of 330. I realize your papers say 30. It was a typo. Please change that to be 330. So, again, plugging in 330. We're going to have to use a reference angle here. So 330 falls into quadrant 4. All schools for your children. So in quadrant 4, cosine is positive. My reference angle would be 30 because we are in quadrant 4, so we do 360 minus 330. So we have a reference angle here of 30. So the cosine value of 30, looking up here at my chart, would be 4 times radical 3 over 2, because we had that 4 out in front. Sine in quadrant 4 would be negative, and then a sine of 30 is negative 1/2. So we get 2 radical 3, negative 2 times negative 1/2 becomes plus 1. So it ends up being choice 3. So it's all about being able to manipulate this chart, dealing with, the sign values, where everything's positive, where it's negative, in combination with your unit circle up there. So next wants to know which of the following is not equal to 1. So here we're dealing with all of the quadrantal values. So cosine of 0, if we look at our unit circle, is 1. Cosine of 360 would also be 1. Sine of 90 is 1, but the sine of 270 would be 0. So choice 4 is going to be the one that is not equal to 1. So then recall that angle and its reference angle have the same trig values. Show by finding the sine and cosine of each angle. Remember how many signs change depending on the quadrant. This little guy right here, that means reference angle. That's another way of being able to write reference angle. So this is telling you what they all are. So what are we trying to find? Sine and cosine, right? Yeah. Sine of 110, cosine of 110. So for 110, it's not using one of our references. It's not using 30, 60, or 45. It's using 70. So you could just use your calculator for these ones and type them in. So the sine of 110 is 0.9397. Cosine is negative 0.3420. Sine of 70 would be the same. However, cosine of 70 It would be the same decimal, only it would be the positive version of the decimal, because 70 is in quadrant 1 where cosine's positive, 110 is in quadrant 3 where it is, or I'm sorry, quadrant 2 where cosine is negative. So for 235, sine of 235 would be negative 0.8192. Again, I'm using my calculator in degree mode. So you can pause and use your calculator in degree mode. So then, sine of 55, again, it's going to be the same decimal, but 55 is in quadrant 1, which is going to make it positive. Same thing with our cosine. So it's the same decimal values, just the signs change depending on which quadrant we are in. Then over here, sine of 282, negative 0.9781. Here in the fourth quadrant, so cosine is positive. Again, our reference angle, same decimal, different value for sine. For cosine, it's going to be exactly the same. So, even though these aren't our specific ones that we use, the 30, 45, or the 60, everything else still works the same. Okay. Let's take a look at the back here. So here we have mini unit circles, as I like to call them. So we are going to deal with this top one. It's going to be the 45s, which in radian measure would be pi over 4. So this would be 0. This would be pi over 4. This is going to be pi over 2, or 2 pi over 4, so it reduces to pi over 2. 3 pi over 4. This would be 4 pi over 4. 5 pi over 4. This was, that's a messy 6, I'm sorry. This was 6 pi over 4, which reduces to 3 pi over 2. 7 pi over 4. And then we finish up at 2 pi. So it keeps following that sequence. So again, as I was saying, this is pi over 4. This was 2 pi over 4, which reduces 3 pi over 4. 4 pi over 4 reduces to that. 5 pi over 4, 6 pi over 4, 7 pi over 4. You reduce where you can. So those are the 45s in radian measure if you are looking at your unit circle. So now this next one, because of where it is, these are the 60s, which in radian measure, pi over 3. So that's 1 pi over 3. This is 2 pi over 3. This would be 3 pi over 3, which reduces to pi. 4 pi over 3. 5 pi over 3. And then our 6 pi over 3, which would be 2 pi. So those are the 60s in radian measure. And then our last one are the 30s. So our 30s in radian measures would be our pi's over 6s. So again, we start at 0. Pi over 6. This is a 60, which as we saw from the other one, was pi over 3. We get there because it would be 2 pi over 6, and so then it reduces down to pi over 3. Then we got our pi over 2 for 90, which again was 3 pi over 6, and then it reduced. So then this would be 4 pi over 6, which reduces. 5 pi over 6, 6 pi over 6, which reduces. 7 pi over 6, 8 pi over 6, which reduces. 9 pi over 6, 10 pi over 6, 11 pi over 6, 12 pi over 6. So they also follow the same pattern, just many more of them reduced than it did with our other examples there. So knowing the radian measures for the special angles, yes, study that. So again, review of radians. We talked about it on day 1. We're going to come back to it again. So 30, 45, and 60. Those are the common ones that you definitely need to know. Quadrantals are the other big ones that you're going to need to know. So, we are going to calculate their exact values when it's in radian measure. Same way we've been doing it before. If you need to, you find your reference angle, figure out in your quadrant what are the sine values. All schools torture children. That's going to be needed. It's again practicing these same skills again. We are just thinking a little bit differently because we are in radian measure. So pi over 2 is 90. So we're looking here for the sine of 90, which is 1. Pi over 3, that's our 60, so the sine of 60 is radical 3 over 2. And again, I'm getting these values off of my unit circle. 3 pi over 2, that's 270, so cosine of 270 is 0. 3 pi over 4. So that means we have 345, so that's a 135. That puts me in quadrant 2, so it's negative. Reference angle is a 45, so negative radical 2 over 2. This one is a multiple of 60 because you got that pi over 3 in here. So that makes this a 240, which puts me in quadrant 3. The tangent of 60 is 3. Here, f of pi over 3 okay, so pi over 3 over 2. Pi over 3 is 60. 60 divided by 2 is 30. So the sine of 30 is 1/2. Plus cosine of 300. So again, 60 times 5, 300. Cosine is positive in the fourth quadrant. Reference angle is 60. So cosine of 60 is 1/2. 1/2 plus 1/2 is 1. So this time we're going with a quadrantal. We're just using pi. So tangent of 2 pi, which is our 360, would be 0. And then sine of 90 is 1. So that gives me a negative 1/2. So reciprocals, again, you got to remember what you're flipping. So secant is cosine flipped. So if I find the cosine of 120, which is what this is. 120 is in quadrant 2, where cosine is negative. My reference angle is 60. So that makes that 1/2. Flip it, and I get negative 2. Cotangent, tangent flipped. So tangent of pi over 6. That's 30. So I'm trying to find tangent of 30, and then I'm going to flip it. Tangent of 30 is that. Flip it. And we end up with radical 3 when we reduce everything out. Cosecant is sine flipped. Excuse me. So 5 pi over 6 is 150. So my reference angle is 30. It is positive because it is in quadrant 2. Sine is positive in quadrant 2. So that is a 1/2. However, I need to flip it. And this little guy here is telling me to square it. So my answer is a 4. So you've got to pay attention to where these numbers are. Numbers in front get multiplied by the values after you figured them out. Numbers here get multiplied by the angles. So here we're doing the cosine of 360 minus the sine of 90. So the cosine of 360 is 1. Sine of 90, oops, I didn't mean to put equals there, is 1. So this makes it 3 minus 1, so I get a 2. So here we got 2 times the tangent of 180 plus the sine of 270. Tangent of 180 is 0. Sine of 270 is negative 1. So I get negative 1. Alright, so then this is going to be secant of 45 squared times the sine of 150. So secant is cosine flipped. Cosine of 45 is radical 2 over 2. So if I flip it, and then I have to rationalize it, my 2's knock out and I get just radical 2. So this is radical 2 squared times the sine of 150. Reference angle is 30. Positive in the second quadrant, so it would just be sine of 30, which is 1/2. I get a 1. Radical 2 squared is 2. 2 times 1/2 is 1. So then our last thing for today, identity, an equation where the left side equals the right side. We did talk about identities with our polynomials unit. It was our last thing. You want to be able to prove an identity to be true by getting each side of that equal sign to be equal to each other. So, a couple of little refreshers. Reciprocals. Cosecant is a reciprocal of sine. Secant is a reciprocal of cosine. Cotangent and tangent. And tangent is sine over cosine. And since cotangent is the reciprocal of tangent, you just flip it. So cotangent is cosine over sine. So, recalling from our unit circle, the sides of our triangle, we're always going from that angle right there. Cosine is x, sine is y, tangent is y over x. So what ends up happening here is we have the Pythagorean theorem. X squared plus y squared equals 1 squared. So I can replace those with cosine and sine. And this has now created what we call a Pythagorean identity. Cosine squared plus sine squared will always equal a 1. So that's an identity that we can use a lot of times to be able to answer questions and solve problems that we have. So we're going to work with that next. These Pythagorean identities can also be manipulated a little bit to get different versions of the same identity. So for example, looking at our cosine squared plus sine squared equals 1. Cosine squared, I could subtract my sine squared over, and then I have the same thing. It's still the same identity, just rearranged. I subtracted my sine squared over. Same thing could happen. You could subtract your cosine squared over, and again, you still have the same identity. It's just written in a different way. Here's our next Pythagorean identity. Tan squared plus 1 equals our secant squared. So once again, we can manipulate it. I can subtract my 1 over, and then I can get that identity there. Tangent squared equals secant squared minus 1. I can subtract my tangent over. So secant squared minus tangent squared will always give you a 1. You can factor a negative 1 out of here and then switch them around. So the tangent squared minus secant squared would be negative 1. So that one's got another extra one that we've seen from time to time. And then our last one, cotangent squared plus 1 equals cosecant squared. I could subtract my 1 over. I could subtract my cotangent over. Or I could factor out a negative 1 and put cotangent first. Again, a few different ways that we could write those identities there. And then they all work. Remember, an identity means it is always equal. Whatever's on the left side equals what's on the right side. So number 1 here, we have an angle has a terminal ray that falls in the second quadrant. If it is known that sine equals that, determine the value of cosine. Oh, please forgive me. My nose is plugging up as I'm doing this right now. Looking for cosine, we are in the second quadrant. So if you remember, all schools torture children. In the second quadrant, only sine is positive. So that means my cosine value needs to be a negative. And so I'm going to keep that in mind as I'm going to solve this. I know cosine needs to be negative because of where we are located. So using my Pythagorean identity that I have up here, cosine squared theta equals 1 minus sine squared theta. I'm going to plug in my 3/5 for my sine. Now that's going to be squared. So then use your calculator, help you figure this out. 1 minus 3/5 squared is 16/25. Because it's cosine squared, it's just like if it were an x squared. You can square root both sides in order to find your answer. And this is going to end up being negative 4/5. So it's negative because, again, quadrant 2, that needs to be negative. Whenever we take the square root of something, if you remember, we get plus or minus. The plus ends up being rejected in this case because we wanted our cosine to be negative because of where we are located. So these Pythagorean identities just make it a little faster to be able to find our answer as opposed to drawing our picture, drawing the triangle in our second quadrant, Pythagorean theorem to find our missing side, and then being able to find our answer. So here, number 2, an angle theta has a terminal ray that falls in the first quadrant, so everything is positive. We have a cosine value of 1/3. Determine the value of sine in simplest radical form. So because I want sine, I'm going to use this form of that first Pythagorean identity, sine squared equals 1 minus cosine squared. So I'm going to go ahead and now plug in my 1/3 for my cosine. So 1 minus 1/3 squared, which is really 1/9, gives me 8/9. So again, I can square root both sides. So this gives me 2 radical 2, because the square root of 8 simplifies to 2 radical 2. Square root of 9 gives me a 3. We are in the first quadrant, so we want the positive. The negative would end up getting rejected. So just using those Pythagorean identities helps us answer questions.